Continuing section 26.7, the formation of images by lenses. So we saw in the last video how to make these ray diagrams for converging lenses as well as for diverging lenses, which is really useful. The other really useful thing is that we can note that there are only a few types of images we'll get, and they always follow the same patterns. So we're going to take a look at some of those patterns. First, we're going to take a look at image formation by a converging lens. And depending on where you put the object, you'll get a different image with a converging lens. So here's an example where the object is placed more than twice the focal length from the lens. So we have the focal length of the lens, twice the focal length, which would be like our center of curvature. It's twice as far away. If we put it out here, every time for any size of object, if it's more than 2 times the focal length away from the lens, then it's going to produce a real image that is inverted, pointing downward, and is smaller than the original object. Pretty cool, huh? Every time. So an example of a converging lens that takes an object that's more than 2 times its focal length is a camera. So this is a classic digital SLR camera, maybe not even digital. And then there's an object, and it passes through the lens of the camera onto the image sensor, right? Where the camera focuses the image and forms a real image that develops your film. If you don't properly focus the camera, then you get a blurry image, right? But assuming that you have the focus set just right, then the object creates, the lens creates a very clear image right on that sensor. And that image is in fact inverted. Your camera automatically flips it for you. And it's a real image. That's why it's able to sense it. It's also smaller, which is good because that means cameras can take pictures of things that are much bigger than what they see on a normal scale, than just what's in front of them. Now, if we instead move the object closer so that the object is between twice the focal length and f, in between 2f and f, in this case, it still produces a real image that's inverted, but it's now going to be larger in the image than the original object. So still real, still inverted. Real and inverted always go together, incidentally. But now the image is larger than the object. It's flipped. And a common example of this is in projectors. So this could be at the movie theater or the projectors in the classrooms. There's a bulb that lights up an object, and that goes out through the lens, and that creates a real image on the screen that hopefully is well in focus, right? So that you can see it clearly. Now, notice the real image here is up, even though we mentioned it's inverted. Well, it's inverted relative to the original orientation. Since the lens is going to invert it, the object is actually placed upside down in the projector, so that it's right side up when we see it on the screen. Okay, so we've seen object outside of 2f, between 2f and f. The last place for a converging lens is between the focal point f and the lens itself. So when we place the object between the focal point and the lens, all of a sudden we now get a virtual image, and the virtual image will be upright and larger than the original object. So a common example of this is a magnifying glass. Magnifying glass, you can look at it, it does have the same shape as this converging lens, and it creates an image of the letters that's bigger than the actual object, than the actual letters themselves. So that's really handy. The other time we get a virtual image is if we have, instead of a converging lens, if we have a diverging lens. So for image formation by a diverging lens, this one's a lot simpler in some regard because no matter where the object is placed, it will always form an upright, virtual, and diminished image. So it's like a reverse magnifying glass where it's making the text smaller, which is what reading glasses effectively are. They're moving the text further away. So we'll get more into eyesight actually at a later section. So stay tuned on that. So we see the diagram formed here that the light comes from the object, and to someone looking at the object through the lens, they see it forming this virtual image that's always smaller. And that's true no matter where you place the object, which is pretty wild. So all of these ideas can be summed up in a single table. Now I know this is a lot of words. This is a pretty dense table. It's okay to put this on your crib sheet. You can use it as a reference when doing the homework or a test, and it's just a nice check. So what we have here is the top three are all for converging lenses, and based on the object distance, we'll know where the image forms. So if the object is outside of 2f, if it's a greater distance than 2 times the focal length, then the image will be somewhere between 2f and f. It'll be a real image, it'll be inverted, and it will be smaller. If the object is somewhere between 2f and f, the image now, it's flipped, is going to be greater than 2f away. It will still be real and inverted, but it will now be larger because of this really nice symmetry that we have with optics. If instead the object is at a distance less than the focal length, between the focal point and the lens, then the image is negative distance, and that magnitude of it is going to be greater than that of the object distance. It's also going to be virtual, upright, and larger. And then finally, the diverging lens, for any object distance, the image distance is negative, and it's always closer than whatever that object distance is. It's closer to the lens. Also, it will be virtual, upright, and instead of larger, the diverging lens produces a smaller image. And we can double check these by looking back at our ray diagrams. So I still happen to have those up here. And we can check, right? So I placed my object at actually an in-between case, 2 times the focal point. And because it's right on 2 times the focal point, focal distance, it produces an image that's almost right on 2 times the focal length and almost the same size. But if I had moved it a little bit farther, then it would have produced a smaller and closer image. If I had moved it closer, then it would have produced a farther image and a larger image. Similarly, for the diverging lens, we see that the object with this diverging lens, the lens produces this image that is smaller and is virtual. It's on the same side as the object. It's not where the real light rays have gone when you're looking at the through the lens. So there you have it. Again, I'm happy to talk about all this. I know it's hard to learn in a remote setting, so please do reach out to me and let's figure it out.